Okay, so hi everyone. Again, a brief introduction. My name is Parnaz Nasri. I'll be your teacher for electric and magnetic fields this semester. And I hope that we can have a smooth semester together despite all the challenges that this current pandemic is causing. Okay, so this is the first module. In the first module, we are going to look at some summary of vector calculus. Actually, I'm going to review vector calculus in just one session. So you are strongly encouraged to look at chapter 3 of your textbook from ULABI edition 8. Textbook, basically fundamentals of electromagnetics. And there are tons of examples there. And today we're just going to review that very briefly and quickly. And then we look at Maxwell's equations, current and charge densities, Coulomb's law, and the rest of the topics. Now, as you saw in the title of the course, it is called electric and magnetic fields. So in this picture here, you see an electric field between two charges, and then you see the magnetic field here, and then also you've heard about gravitational field, right? But what is a field? Well, first thing you can imagine by hearing a field is maybe this picture or a soccer field or something like that. But in physics, what we mean by a field is that it's a region of space, and at each point of this space, there is a physical quantity that is associated with this point. So right here, a physical quantity, phi, or I'm going to call it F, doesn't matter. You'll see that in a bit. So for example, here in this map, you see this map, and then also there are some numbers on different regions of this map, right? You see 11, 13, 14. These numbers are actually showing the temperature of different regions on this, in this space or in this map. So we call this a temperature field, because now at each point of this space or this region of a space, we are associating each point with a number, and that's a temperature. Since the temperature is just a value with no direction, we call that a scalar field. So a temperature is a scalar field. Unlike a scalar fields, there are some fields that have both amplitude and directions. For example, on the same map, you can define another physical quantity, like wind. For example, in this region, now the wind is in this direction, and in this region, it's in this direction. And here, this direction. Different vectors, as you can see, they have different lengths representing their different amplitudes. So for example, this can be, I don't know, 20 km/h wind. This can be 10 km/h, for example, something like that. So this quantity, physical quantity that is wind, has both direction and amplitude. That's why we call it a vector field. Okay, so far we learned what a field is, and we saw that we are mainly concerned with two types of field in this course. One of them is a scalar field, and then the other one is a vector field. Now, when we go back to the electric field and magnetic fields, I think I loaded a previous version of my slides, but anyway. So when we look at the electric field and magnetic fields here, for example, at this point, the electric field has this direction with this value. Here, we have this direction. Magnetic field is the same. So what kind of fields are electric field and magnetic fields? Are they scalar or vector? Yes, thank you for the quick answer. They are vector fields. Great. So now but we can relate them to some concepts that we know from circuit analysis. For example, in a circuit analysis, you know about R, L, C, and then some voltage source, for example, here, something like that, right? So in circuit analysis, you know, R, L, C are your components. And then you have, you measure or you calculate two different quantities known as voltage and current. Now, you can easily associate or connect these concepts that you know from circuit analysis to the concepts of electromagnetics. In electromagnetics, we are, as by now you know, we are interested in electric field and magnetic fields that are vector fields, basically. And basically, our components are actually permittivity, permeability, and sigma. These are the things that you will learn in this course. Permittivity of a medium acts like the capacitor. So I'm going to call this permittivity. Then this one is permeability. This sigma is conductivity of the material. Okay, the conductivity acts like the resistor or similar to resistor. Permeability is like an inductance. And interestingly, you can even say that the electric field, you can see the correspondence of these concepts through their units. What is the unit of voltage? Do you remember? You're electrical engineers now. What is the unit of voltage? Volt, right? And then current is ampere. Electric field is volt per meter, and magnetic field is ampere per meter. So you see, very close concepts here. Now, this is just to show you or connect these new concepts to something that you know previously. They're not very different from what you know before. But as I mentioned, in this course, we are going to look at electric field and magnetic field and their calculations. Now, since these fields are vector fields, we are specifically interested in performing operations on them. And what encompasses vector representation and vector algebra or differentiation and integration is basically called vector calculus. So we learn how we represent a vector and then how we add them, subtract them, multiply them. And then something that is new to this course, and you might not know it from before, is gradient of fields, divergence, curl, and then some theorems that helps us basically solve different physical problems. Any questions so far? I guess these are pretty basic for you guys. Okay. Now, in order to talk about vectors, define them and show them, and even define a point in space, which is what we're really interested because we are studying fields here, is that we need some coordinate system. We need some tool to define these points and vectors in it. And what is very useful is a three-dimensional coordinate system. So three-dimensional coordinate system is very similar, or you've seen an example of it as the rectangular or Cartesian coordinate system, X, Y, Z, right? You can define points in it. You can define vectors in it. And the more general case would be if you had, let's say, I'm going to call this U3 hat, right? So any system that has 3 dimensions can be used for our purpose, but we are specifically interested in orthogonal 3-dimensional coordinate systems. And 3-dimensional coordinate systems means that the 3 axes or the 3 variables that would define the points and vectors for us are basically like going to be orthogonal to each other perpendicularly. Now, each coordinate system or orthogonal coordinate system has 3 base units, base vectors or unit vectors, we call them. So these are unit vectors. And what do these unit vectors mean? First of all, from unit, what do you understand from unit? When I say this is a unit vector, what does it tell you?
1.
Exactly, thank you. Yes, magnitude is 1, right? So immediately when you hear an orthogonal coordinate system is composed of these unit vectors, what you can say is that amplitude of U1 hat is equal to amplitude of U2 hat and then U3 hat, and they all have magnitude of 1. Now, something that is very specific to orthogonal coordinate systems is that we said they are mutually perpendicular together, these unit vectors. Do you remember how we define perpendicularity of 2 vectors?
We cannot express.
I'm going to refresh your memory. I'm going to write it right here. Let me finish this slide. I'll go back to your question. So for example, when we say vector A is perpendicular to vector B, if you remember, that means that the dot product of these 2 vectors is going to be 0. That also means B dot A is also 0. So I hope you remember this. And then dot product, again, just a review is that when we want to calculate A dot B, we are basically projecting A onto B. So this value would be A dot B. So when we say 2 vectors are perpendicular, like this, as you can see, if we project them onto each other, there will be no value, 0. So this is just a little bit of review. So when we say 2 vectors are, these unit vectors are perpendicular to each other, what does that mean? That means that U1 hat dot U2 hat is 0. The same thing for U2 hat dot U1 hat. Then U1 hat dot U3 hat is 0. And U3 hat dot U1 hat. Then the same thing for U2 hat and U3 hat. So you see, we translated this mutually perpendicular axes to something that is mathematical, right? I don't know what's happening to this. Now, another important thing about orthogonal coordinate systems is that these unit vectors compose what we call like a rotation circle. For example, if you write U1 hat here, U2 hat here, U3 hat here, and imagine the circle that has a direction actually, What it means is that let's go to our right-hand rule. I'm not a good drawer, but so imagine this is your right hand, right? If you go from U2 hat to U3 hat, your thumb would show the direction of U1 hat. Now the same thing for U1 hat to U2 hat. Again, right-hand rule, if you go from U1 hat to U1 hat to U3 hat, U2 hat should be in the other direction. So imagine this is a hand actually. So my direction is here actually is kind of wrong. And it should have been the other direction. So orthogonal coordinate system, we can say that U1 hat cross U2 hat is U3 hat. Then U2 hat cross U3 hat is U1 hat. And what else? U3 hat cross U1 hat is U2 hat. Now, does anybody remember when, if we calculate U2 hat cross U1 hat, what would that be? When you reverse the cross product,
Negative
exactly,
U2 hat.
minus U3 hat. So whenever on this circle, you go to the opposite direction, you go this direction, you have to consider the minus sign of this basically vector. Then U3 hat cross U2 hat minus U1 hat, U1 hat cross U3 hat will be minus U2 hat. So this is very useful when you're calculating curl of vectors or the cross product of vectors that are specified in unit vectors. Basically, you'll see examples of those. So this circle is actually very useful. Now let me go back to a question here. Why is it uniquely, so Leo is asking, why is it uniquely important, the last slide. So let's go back here. Why do we need to uniquely specify locations of points in a space? Because we want to know things exactly where they are, right? When we are solving problems, if there is an ambiguity about points where the sources are or where how the vectors are directed, then how can we solve that problem if we can't state the problem clearly and uniquely? I hope that answers your question, Leo. But because we want to solve problems exactly exactly and accurately. Okay. Now, there are some commonly used orthogonal coordinate systems. One of them is Cartesian, or what you might have heard as rectangular. Then we have cylindrical, spherical coordinate system. So in a rectangular coordinate system, as the name suggests, we are looking at the axes of a rectangular box. So like X, Y hat, Z hat. In a cylindrical coordinate system, we are basically interested in the physics that or in the problems that the geometry of the problem can be solved through a cylinder. So we are looking at a cylinder here. And a spherical one, as the name suggests, we are looking at a sphere. So I'll go through the details of these coordinate systems next. Do you have any questions so far? Okay. So in a rectangular coordinate system, system, which I assume you're mostly comfortable with or work with, we have three unit vectors, x hat, y hat, and z hat. These are the unit vectors. Now, we know based on the properties of an orthogonal coordinate system that these are perpendicular to each other. So whenever we say, so we can say x hat dot y hat dot x hat is 0, and the rest of it, right? We can also say that, sorry, I don't know why this is moving with my hand. The cross circle is going to be like this, x hat, y hat, z hat. And so that means that x hat cross y hat is going to be z hat, y hat cross z hat is going to be x hat, z hat cross x hat is going to be y hat. And yeah, so now let's look at a point presentation in this. So I'm going to define point P here. Sorry. Point P here. So in order to uniquely define the position of point P using this coordinate system, I'm sure you're very familiar with this. We can say, what is the height of this box that we drew here? And P would be defined using 3 variables. One of them is this projection and then mapping it to x-axis, the other one projection on y-axis, and then z-axis. So for example, here, just looking, we can say that x is 1 plus 1, y is plus 4, for example, and then z is 2, right? So we need to define the position of the point P using these 3 variables, x, y, z. Another important thing is that to define this a vector in this coordinate system, let's call this vector A. So if I tell you that if you project the beginning and end of this vector, this is plus 1, this is plus 2, and then come here, project it again into xy plane, and we get, let's say, this vector. This is, for example, plus 2, this is plus 4. This is also plus 1, plus 2, for example. So I projected all of the beginning and the end of this vector, point A and point B, point beginning and end of it, to all the axes. Now, if I want to define A, how can I define it in terms of the unit vectors? Let's just start with this direction, in x direction. In x direction, it has started from point 1, it ended up with point 2. So that's going in x hat direction with the magnitude of 1. So that's 1 x hat. Now in y direction, this vector is also moving. How much should I put for y hat? Let's assume this is 4. Have I lost you guys? So in a vector, we always put it, we consider the beginning and the end of it, right? So it started from 2, it ended up at point 4. So that means that it went 2 units in y hat direction. Now let's go for z hat. How much this vector moved in z hat direction? Exactly, 1 z hat, because this started from point 1 in z axis and it ended up, let's say, in +2. So you see, when you're defining a vector in the rectangular coordinate system, you need to define it in terms of x hat, y hat, z hat. For example, if I give you vector b here, and I say it's actually minus y hat plus z hat, and we want to draw this vector. How does it look like? So we know, let's assume that this is the beginning of vector b, doesn't matter. And then we have to move 1 unit in minus y hat direction. So that's 1 unit in this direction. And since this is the positive y hat, we have to go to the opposite direction. Then we go 1 unit in the plus z direction. So we go to here. So that means this is z hat, this is minus y hat. And then that would mean that our vector b would look like this. So if you look at the x direction, it's not moving in x-axis at, like, you see, the x is constant and b is only moving in y direction and z direction. So this is how we draw things and interpret a vector that is composed of different unit vectors. And so now what matters is that, let me check the time. Okay, now what matters is that we have to define volumes and surfaces in rectangular coordinate system. So as you can see in this page, I'm going to draw it again here. So in order to define a volume here, you can see it in this figure here as well, but I'm going to draw it again. So if you move, if you change the x variable, we end up with this. If we change, sorry, this is y, this is z. Then if you change y, we end up with this. So we ended up with a surface. Now, if we change z, we end up with a box. Right? Now, with this box. So now we know this length is dy, this length is dx. The height of the box is also dz. I'm sure you can calculate the volume of this box. dv is going to be dx, dy, dz. So whenever you're calculating things or integrating things over a volume in a rectangular coordinate system, you have to remember how to divide it in different directions. Now, it's easy to calculate it for surfaces as well. For example, for the top surface, only dx and dy are changing. So the value of the surface or the amount of surface is going to be dx, dy. Now, another thing that matters is we're going to look at flux through surfaces. So that's why we need to know the vector that is perpendicular to a surface. So for example, here, we know that the surface the vector that is perpendicular to the x, dy surface is actually z hat. It can also be minus z hat, right? So when we're defining things, or when we want to, for example, calculate the flux through a surface, we need to know the direction of the surface or the direction that is perpendicular to the surface. So that's how we define it. I'm going to move to cylindrical coordinate system like this one. So in a cylindrical coordinate system now, as I reviewed it very quickly, we imagine things in cylinder. For example, let's look at the coordinate system that we had, x, y, z. X, y, z. Now we want to define the position of point P but in the cylindrical coordinate system. How do we do that? What we do, we imagine a cylinder that passes through P. So this is the cylinder. This is the cross-section of the cylinder. This is the height of the cylinder. So now how can we define this point P here in imagining that it's on a cylinder? Now, if you look, first thing that comes to mind is we can define the height of the point P, right? Just like what we had in the rectangular coordinate system. So we have Z. Now, something else that we have is, let's project this point on XY plane. So this is X, this is Y. Let's imagine point P projected on this circle going to be on this point. Now, in the cylindrical coordinate system, instead of indicating the position of point P in terms of X and Y, we define it in terms of the radius of the cylinder and also the angle that it has from the x-axis. So we call it rho and phi. That way, we can also uniquely define the position of point P. So in the cylindrical coordinate system, we have rho, phi, z. Whenever we define the variables of the coordinate system, then immediately we can define the unit vectors for it as well. A more general definition of unit vector can say that the direction or the direction with the magnitude of 1 when the variable changes, increases for a very small amount. Increases, so we always go to the direction of increasing for small amount. So for example, in when we define z hat, let's be reminded that we want to see how at this point we want to see we want to go to the direction that z increases, so that's going to be z hat because z increases in this direction. The same thing for x hat and y hat. Those are easy because x hat at each point in the coordinate system, x hat, y hat, z hat always increase in the same direction. So they're constant vectors. But here, let's look at it here. For example, here, if you want to say rho, we know the unit vector of z is going to be z hat. But for rho, if rho changes, increases for a very small amount in this point, rho hat is going to be in this direction. And phi hat is going to be in this direction. For a very small amount, if phi hat changes, is going to be in that direction. So this is going to be rho hat and phi hat. So these are the unit vectors of a cylindrical coordinate system. Now, unlike x hat, y hat, z hat, if point P was at a different point, was at, let's say, this point, then when we define rho, rho is going to be this direction, or it's going to be connecting to P to the center in this direction, and this is going to be phi. Right? We still have some time. So that means that rho hat is going to be in this direction now, and phi hat is going to be in this direction. So you see, depending on the location of point P, rho hat and phi hat are changing. That's a very important point to consider. Although they're always as the unit vectors of this orthogonal coordinate system, although they're always orthogonal to each other, so rho hat point phi hat is going to be 0, rho hat point z hat is going to be 0, phi hat dot z hat is going to be 0, but their direction changes. We can also define the circle of rotation for this unit, for this coordinate system, just like this. So right-hand rule. So for example, here, if you want to find what is z hat direction, again, right-hand rule, fingers from going here to here, then your z hat direction would be out of the page, right? Okay. I hope this is clear. And we can definitely find rho hat and phi hat in terms of x hat and y hat. These are going to be in a table in your textbook. Now, in order to define a volume in cylindrical coordinate system, you can see that the volume looks like something like this shape now. And so when we are moving in r direction, dr is going to be like this. This basically, this change will represent the change in the radius. This change obviously is going to be dz because it's changing z direction. Now, something that might be not very clear at the beginning is r d phi. So for example, on a circle, when you want to calculate how much is the length from here to here, you can't simply say this is d phi, right? First of all, d phi is not a length identity. In order to calculate this, this is basically r d phi. So that's why the different sides of this volume are going to be r d phi, dr, dz. And the volume itself, that is going to be the multiplication of all of these lengths together, r dr, d phi, dz. Okay, I'm going to stop here and to see if you have any questions. I'll be available, and hopefully we can cover the spherical coordinate system and the rest of the content for in the future lectures. Any questions?
Hello, yes, may I ask a question?
Okay, if you don't, let me stop recording then. Oh, there is a question. Hi, Leo. What's your question? Well, you have to, basically you have to map it to a coordinate system. It might not be as easy as basically as clear as defining it in a cylindrical coordinate system or something else, but basically you have to define a coordinate system that is not necessarily any of these ones. For example, it can be, as we mentioned, u1 hat, u2 hat, u3 hat. You have to find an orthogonal coordinate system, and that would help you to solve the problem. So cylindrical, spherical, and rectangular coordinate system are the most commonly used, and what you will solve the problems with in this course. But definitely, if you have a more complicated, oh, we still have 10 minutes? Okay, I didn't know. If you have a more complicated problem, then you have to define your own coordinate system. And then write all of these rules for it, basically. Okay, if you have 10 minutes, so that's good that I didn't stop recording. Let's go to the spherical coordinate system. Leo, if you have more questions, I'm happy to answer it after the class. I'll show you the slide about the table. Okay, so in a spherical coordinate system now, in the spherical coordinate system, as I mentioned, we have to define 3 variables and 3 unit vectors. So let's say X, Y, Z, and let's imagine a sphere, because that would help us define the position of this point P. And now this doesn't look like a good sphere, but the sphere has to be centered at the center of the coordinate system. So then what we can define first is obviously the radius of this sphere. So that, let's call that R. And then what else can we define? We can also define the angle from the z-axis. We call that theta. Then another angle that would help us define this very uniquely is as when we map this or project this radius or this line that connects the center to point P on XY plane. On XY plane. Then, similar to the cylindrical coordinate system, we can define an angle phi. Can somebody tell me, it doesn't look from the picture, but if this is R and this is theta, this angle is theta, how much is the projection of this line on the XY plane? Exactly. Thank you, Leo. I think it's Leo, right? Yes. R something theta. Well, it's sine theta, right? So because let's imagine, I hope this is not too confusing, but if we imagine a rectangle with a right corner here, and let me show it. Doesn't matter that it is rotated. This is an angle, this is theta, this is R, then the projection is actually this length. So you can say this is R sine theta. So this length would be R sine theta, right? This is a useful variable to know. This, I'm going to call this prime because it's a projection of point P on XY plane. Okay, so now that we established, we need 3 variables. We call theta, phi, and phi. We called theta phi and called phi theta. No, remember, in this course, theta is always going to be the angle between z-axis to the point, and then phi is going to be, just like the cylindrical coordinate system, is going to be the angle from x-axis to the point. Okay, so that's very important to remember. And what else did I want to mention? Sorry. Okay, so now we have to define the unit vectors. So at this point, this is too busy. Let me draw another one. X, Y, Z. And this is our point P. We established that this is R, this is theta, and the projected one, for example, this is phi. So for each variable that we define, we are going to define a unit vector. Yes, theta is the angle from z-axis to the point. So r hat is going to be, again, in the direction that increases the variable r. Okay, we can't do. So r hat is in this direction. Again, if we want to increase theta, we have to move in this direction, right? So theta is going to be, theta hat is going to be in this direction. And then phi hat is more complicated. If we look at it here, again, increasing phi hat is going to be in that direction. and it's in XY plane. So let me draw it with this one. So phi hat, if I want to draw it exactly at this point, is going to be right here. Another important thing to know is that, again, r hat, theta hat, and phi hat are going to be in this circle. So whenever you forget like how to calculate phi hat, use your right hand to go from r hat to theta hat, and then your thumb would give you the direction of phi hat. So at this small coordinate system here, I hope you see it with my pen, this is what's happening. If I go from r hat to theta hat, phi hat is the direction that my thumb would show. So just like other coordinate systems, orthogonal coordinate systems, r hat dot theta hat is 0, r hat dot phi hat is 0, theta hat dot phi hat is 0. And I'll explain it. Phi hat, r hat, sorry, theta hat cross phi hat is r hat, and then phi hat cross r hat is theta hat, right? Okay, so, somebody is asking, how do we get the direction of phi hat? Did I read that question correctly? Yes. So remember, phi is basically defined in XY plane, and it is the angle that connects the x-axis to the line that goes from center to the projection of point P. And any unit vector has to be in the direction that increases that variable for a small amount. So at this point, phi hat and P prime, let me go to XY again. So this is the projection of XY. This is point P prime. And then we established that this is phi hat, angle. So if phi increases for a very small amount, just like this much, right? How do you connect these 2 points? You connect it like this. So this would be the direction of phi hat. This is the direction that phi changes for a very small amount. And you can say this is going to be perpendicular to this line, basically. Does it make sense? When we see R, it implies a spherical, whereas when we see rho, it implies cylindrical. Yes, that's exactly correct. Thank you, yeah. Yeah, so this is what we are going to use in this course. I know every year they have the same problem, like in the previous courses, they use a different standard, but in your textbook and here through the lectures, we are going to use these conventions. Because we are using this textbooks for you, and then in the problem sets and every the examples that we solve, this is the convention they're using. So in order to not confuse you between the textbook and the lectures, we are sticking with the textbook convention. Okay. Okay. Well, I'm a sessional instructor, and yeah, I think that they haven't been able to solve this problem for a long time. Because every year I hear the same thing. But if I had the power, definitely I would have root for you to not be confused this much with the coordinate systems. But okay, so I think we can stop now, and then I'll stop recording as well. Next session, we quickly just go through this and then also continue with a spherical coordinate system and the rest of it.